Hey folks, this is Todd Coburn with your Aerospace Structure series. This lecture is on torsion and twist of non-circular sections. We saw last lecture how a round section experiencing torsion will have a shear stress equal to TR over J, which grows from 0 to the max value at the extreme radius, 0 at the centroid, max value at the extreme radius, in a linear fashion as we see here. And it also experiences twist TL over GJ, where J in both cases is the torsional constant, which for round sections happens to be the polar moment of inertia. So we see section A here is a round section which can use that methodology. All the rest of these are also, and even more common, aerospace kind of cross sections that are used for any kind of lightweight structural design, which actually includes civil and mechanical as well. All these others are non-round sections, cannot be used. We cannot use the same methodology as we have for round sections without introducing significant error. So we're going to learn how to evaluate those when they experience torsion. The problem with non-round sections is because they have such a low torsional rigidity that they deform when they twist. They twist easily, they twist a lot for a small torque, and they distort and deform under that torsion. The problem is, if you look at a round section, you can see that when we apply a torsional load, the stress that develops can move around the cross section in a continuous manner. We get a linear distribution of stress and strain going from the centroid to the outside. And because it can continue on around without being stopped, it doesn't have to turn back on itself. It's very efficient. Now, if we have a rectangular section, we're going to find a similar thing, but now we find if we draw a tangent to any point, going back to our round section, you can notice under the experience of this torque, for any little element here, it has a stress going like this, and it can move straight into the next adjacent element, and so on. Not so with a rectangular section. We can kind of do that thinking, okay, if we're here near the centroid, we can move like this. But if we get out this way, once we get out in here, a little element right here can't move like this. It can't do that. It has to turn back on itself. What this ends up doing is it ends up making a nonlinear distribution of stress. The shear stress here can build up to some max value in something that is not linear anymore. But when we get out here, there's got to be a zero shear stress, which means our shear stress, which was building up, now has to drop back off to zero. This causes significant twisting and distortion of the cross section. This is a rectangular section, so it's not as severe as if we have a thinner rectangular section. So we're going to end up with stress distributions looking kind of like this. This is actually drawn linear there, but it's actually not. It would be nonlinear. What we can end up seeing is kind of, if we actually inscribed a circle of this diameter and used our TR over J, we would probably be maybe a little bit conservative because there's a little more material. But we're also going to have distortion of the element. The more narrow the section gets relative to the other dimension, the more distortion we're going to get of the material. Now, if we look at a thin-walled section, as we see in many lightweight structures like aircraft, you'll see that now, once again, looking back, we notice that any stress can move around that round element and continue to be reacted by the next element. It can, if our section is square, it's distorted a bit, but it actually can follow nearly the same relationship. You'll notice because for most of this, you can keep going around, but as it gets narrower and narrower, you'll notice that any shear stress moving into this flange can't go like this. It has to come back, turn and come back. it's kind of like this behaves like a bunch of little round sections where each one can resist a little bit of torsion, or a little bit of torsion, a little bit of torsion. If you inscribed a bunch of little circles in here, it would be very similar to the way this behaves, with each little circle withstanding a little bit of that torque. The torque builds up through the thickness, but it has to drop off down here at the end. So you're going to end up getting a maximum value near the center of each flange, at the extreme fiber near the center. If you picture that flange, if we blow that flange up, and you imagine these little inscribed circles, and each of these little inscribed circles is going to be something similar to a round section of that size, but as we move further out in the flange, it gets less and less and less, because the rigidity to this kind of torque becomes less as this thing also sags and distorts and twists. So this ends up causing a change in the way the load is carried in a much less efficient manner. It's kind of like if you have a large room where people can move around in a circle, maybe holding hands, versus if you have a narrow hallway and the food table is at the far end, they have to go down and then they have to turn around and then come back, and they're resisting, and somebody always wants to turn back and they can't because there's too many people. They got to go all the way back and then turn back around. It's very inefficient. The same way, thin sections are very inefficient for carrying these kind of torsional loads. So we see for round section and non-round sections. With the round, we had linear and elastic deformations. We assumed that plane sections remain plane and undistorted. The material was assumed to be homogeneous, isotropic, and elastic. But if we have a non-round section, even though we may have a homogeneous, isotropic, elastic material, our stress and strain are no longer linear functions. Our plane sections no longer remain plane. Our cross sections are distorted. This is illustrated by a couple pictures out of Hibbler's text, the kind of twist and distortion we may get. Now, some years ago, back in 1903-ish, Prandtl noticed that the equations for the torsional stresses in a non-round section are similar to the equations for a membrane experiencing load. If you imagine a balloon that you blow up and how that balloon billows. Now imagine that you have a square frame and you have a thin balloon-like material and you apply pressure. Now if it were round boundary, it would have a nice uniform depression down to the maximum value. But if that frame is square, you can see that you're going to kind of get a circle through the inscribed circle into the smaller dimension, but as you get near the corners, you're going to get a little different. It's going to tweak up the deflected picture. And the equations that represent that are similar to the equations for torsion. For this reason, we call the approach a membrane analogy for our shear stresses. And we're going to end up finding that our shear stress is Tt over J, where J is the torsional constant, and TL over GJ, but J is now a different torsional constant than for round sections. We're going to cover this in more detail in a moment. So let's just imagine a thin bar experiencing a moment or a torque. We already pointed out that our stress and strain are no longer linear functions. Our plane sections do not remain plane, and cross sections get distorted even if our material is homogeneous, isotropic, and elastic. Our key equations are going to be that the shear stress at any point is Tt over J. And actually, even though we can analyze for the shear stress at any point in a round section by just plugging in the R, when we deal with a non-round section, we basically are just going to calculate the shear stresses at the maximum spot, which is at the middle of the flange. If you imagine just like that shear stress in the round section got larger as you moved away, the same thing's true for the non-round, but now, remember, imagine we got little inscribed circles, And the circle that carries the most torsion is the center one near the CG of the thing. And every other circle is similar, but as you move away from that, because this thing is going to also defend under this torsion, it's also going to kind of noodle out, kind of deflect like a noodle. So there's going to be less torque moving out as you get further and further out the flange. For this reason, the center of each flange will be where the shear stress will be maximum. It'll be at the extreme fiber of the center of each flange. Now this rectangular section only has a single flange, therefore you can expect the max stress will occur right there, if this is the bar, at the top and bottom at the middle of that flange. And the value of the max shear stress will be Tt over J, where T is the torque, little t is the thickness of that flange, and J is the torsional constant of the entire cross section. In this case, this cross section only has a single flange. Now you'll notice I use this alpha subscript for J. This is the torsional constant. It is no longer the polar moment of inertia, and we're going to find that the torsional constant for shear stresses and for angles of twist can be different values. The angle of twist will be TL over GJ. Now, fortunately, you'll notice this, both these equations have the same form as we saw for round sections. For round section, our equation for stress was TR over J, and now for non-round sections it's TT over J, where T is the minimum dimension. So if your section is B by T, then T is the smaller dimension. If it's 1 by 2.1, if it's 1 by 0.1, then 0.1 is your T dimension. If it's 5 by 3, then 3 is your thickness dimension. Whichever dimension of the flange is the smallest, that's it. Now you'll notice we have a little subscript I for the shear stress, and the reason is that each flange, we're going to get the torsional constant of the whole thing, but each flange will experience or could experience a different shear stress distribution. In each flange, we need to check what the shear stress is. The max shear stress in that flange will be T on the whole section over J on the whole section, multiplied by the thickness of the flange. So we're going to find that the thickest flange will end up carrying the most shear stress. For angle of twist, you'll notice this equation has the same exact form as we saw for round sections, TL over GJ, but instead of J being the polar moment of inertia, J is just the torsional constant, which may be the same or different than the torsional constant for shear stress. So the question is, what's our J? Well, J is going to be the sum of the alpha BT squareds, where for each flange in the cross section, we're going to figure out what is our B, what is our T. B is the width dimension, the larger dimension. T is the smaller dimension. We're going to calculate the B over T ratio and calculate the alpha for that flange. We're then going to take the alpha BT, and that's how much contribution that flange makes towards the total J of the section. In our example here, we only have a single flange, so there's only one term. If we have a angle, we're going to have 2 terms. If we have a Z, we're going to have 3 terms, and so on. Okay? If we have if we need the angle of twist, we're going to calculate a different J. It's got the same form. It's the summation of the beta BT squared. So we're going to calculate our B over T ratio for both. B is the same for both of these. T is the same for both of these. The B over T ratio is the same. But then we will look up the alpha and the beta and multiply each quantity by those values. The summation of the alpha BT square cubes is our J for the shear stress, and the summation of the beta BT cubes is our J for the angle of twist. So you ask yourself, well, where do we get our alphas and betas? Well, right here. We're going to look up our B over T ratio, and we are going to read the alpha and the beta. So if we are square, that means B over T equals 1. Then you'll notice that alpha is 0.208 and beta is 0.1406. If we actually have a B over T of 5, you'll notice that the alpha and the beta look the same. They're actually not the same, but they're the same to 3 decimal places. If we have any B over T ratio greater than 5, we can use this approximation that the alpha is approximately equal to the beta, which is approximately equal to 1/3 times the quantity 1 minus 0.63 over B over T. If we have anything in between these values, like 2.25, then we need to interpolate in this table for the value and use that. So what we see here is that if a flange has a relatively long width versus its thickness, like if it's 5 by 1, then its B over T ratio is 5, and your coefficients are 0.291 for both stress and angle of twist. If our flange is, say, 1 inch by 0.1 inch, then our B over T ratio is 10, and you would use this equation, 1/3 times 1 minus 0.63 over 10. Okay? That's how you get your alpha and your beta. Once you have your alpha and your beta, you calculate the J of each and every flange, you add them all together, and that gives you the J of the cross section. Then you calculate your stress T of each individual flange. So if I have an angle, I'll take T this thickness over the J to get the shear stress in that flange, and T torque times this thickness over J to get the shear stress in that flange. Once again, the J is of the entire section. We're going to be checking the stress in each flange by taking the T of each flange. The torque and the J remain unchanged. That's the same for the whole cross section. And for each flange, we'll then multiply by the thickness, little t, of that flange to get what the shear stress in the flange is. That's how we do it. We'll see some examples. Okay. One other thing is worth noting. If you get much larger than 10, then eventually this alpha and beta both approximate 1/3. So a lot of times in industry, we'll just grab 1/3 if we have thin flange members, similar to what we see in aerospace. But actually, you would use this equation that I'm giving you here at the bottom of the page to calculate the precise number. Okay? All right. So if we ask ourselves which of these methods, which of these sections need the non-round method, we would see that all of these except for section A need a non-round analysis. If we look at section B, we can see there's only a single flange, so that means for either of those sections in B here, figure B, that means we'll only have one term in our J alpha and our J beta. This angle, you can see we're going to have two terms, one for every flange. For the C section, you see the first C section, we're going to have 3 terms. The second C section, we're going to have 5 terms. 3 terms for the first J, 5 terms for the second Z. Did I call that a J? The Z section. For the T section, looks like we've got 3. For the J section, looks like we've got 4. I section, there's a few different ways we can idealize it. We could idealize it like this. 1, 2, 3. Or we can do it like this. 1, 2, 3, 4, 5. This has the benefit of you can go on and calculate your properties for doing other stress analysis. This one, you'll notice we kind of end up double counting some areas, but I believe this is a better method of evaluating the angle of twist of non-round sections. And the reason is this does a better job of representing the stiffness of this flange under the action of torque. So I recommend breaking this up from the end to the half thickness, from the end to the half thickness. That gives you your B1, B2. Then we're going to go from the half thickness to the half thickness. The thickness, that will be B3. End to the half thickness, B4. Half thickness to the end, B5. And then the T is just the thickness of each individual flange. Okay, we'll see more of this as we move on. Which of these J's are actually the polar moment of inertia? Well, only that section A, which is round, whether it's hollow or solid, those will be the torsional constant is the polar moment of inertia, but not for any of the rest of these. Which of these sections will distort when twisted? All except for A. Any non-round section will distort when twisted. This is where we're going to talk about our best idealization. If we have a J section, we can have A, which is going from the edges to the half thicknesses, B, which does not double count for anything, C doesn't double count for anything, and D, which doesn't. Now we'll see here that I believe the best idealization for torsion, and the one that I expect my students to use, will be cross-section A, where we're going from end to half thickness. B and C have the benefit of actually not double counting for any area, so they're good if you need to also calculate, say, bending of the section and other section properties. D is the fastest and easiest, but I believe gives a little less accurate value. Okay, all of these methods of idealizing can be seen by people's work in industry. We said that, we said this, and we said this. Okay? Where are the stresses maximum? We talked about that as well. This is our shear stress equation, and we saw our distribution of stress was nonlinear. It has to be 0 at point B. It can peak up at point A and point C, but you'll notice that at A, which is the surface of the center of the thickest flange, that's where we're going to see the highest stress. If we have something like this, you can see once again, we're going to get a local maximum stress at point C and the opposing point on the upper flange, at point A and H on the middlemost flange, and at point N and J on the lower flange. We would calculate the T of the whole section, the torque. We would calculate the J, the torsional constant of the whole section, and then we would multiply by each thickness in order to get the max shear stress in each of these flanges. If you ask yourself which one has the maximum stress, if you look at your equation, T over J, if the torque is the same for all spots and the J is the same for all spots, and it is, each of these flanges contributes a piece of the J, but the total J is what you use in this equation. But then we plug in our thickness of each flange. You can see that the thickness of the thickest flange is going to cause the highest shear stress. So the max shear stress for this part will be at point N and point J, where the flange thickness is the largest. Got it? And this is showing our little analogy of these little balls, these little round sections. And we can see this middlemost one will have the most torque carried, and the furthest is the further away we get, the less we have. Okay? All right. Now you'll notice here we've got 3 sections. Each of these will use our, we talked about the length of each flange being measured from the end to the half thickness. And if we want to analyze these, we're going to construct a table. So for section A, the angle, we would only have 2 flanges, B1 and B2. Now you'll notice these are labeled. What we would do here for this one is we would go from the half thickness to the end. That's B1, and from the half thickness to the end. So if this dimension is 2 inches and this dimension is 3 inches, and if this flange is 0.2 and this flange is 0.1, then actually element 1 would have a length, a B, of 3 minus half of 0.1, so 2.95. The thickness is 0.2. The B over T is just this over this. We can populate that. For element 2, we see we've got 2 minus half of the thickness, which is 0.1. So that's 1.9 is our B dimension. our thickness is 0.1, our B over T then, we can calculate that. We can then look at the B over T ratio and calculate the alpha and the beta. Look at the B over T ratio, calculate the alpha and the beta. The alpha times BT cubed is our J alpha, and the beta times the BT cubed is our J beta. We calculate the same two values for this. We sum these up, and that is our J alpha. We sum these up, and that is our J beta. We can now calculate our stress in each flange. What we're going to do is take the total torque on the section, divide by the total J of the section, and if we're doing shear stress, we're going to use J alpha, this value. We then multiply this quantity, which is the same for both of these, by the thickness of first one, and then for the other one, it'll be multiplied by the thickness of that flange. The max shear stress is not adding these together. It's whichever of these two values are maximum. That goes down here. For the alpha, we're going to take the T on the total section, the L of the total section over G of the total section, and the J beta of the total section. And that is our angle of twist, which we can write right here. That will be in radians. So if we want to convert that to degrees, we will have to multiply that by 180 degrees per pi radians, and that will convert us, or 360 degrees per 2 pi, and that will convert us. Now, if we had instead analyzed the second one, we would idealize it as 1, 2, half thickness to half thickness 3, end to half thickness 4, end to half thickness 5. We'd end up having 5 values in our table, and the process is the same. We did this one here. Our element 1 is going to be from half thickness to end, half thickness to half thickness to end. 3 elements in our table, and the rest of the process is the same. That's how we do it. This slide, my students don't need to know this, but this is a good thing to understand. What we end up doing, we find in aerospace, a lot of times there's a chance for load to be introduced into these thin members. But because they're so flimsy, they really don't pick up any torsion, negligible torsion. As soon as we start becoming a better analyst and we see that a force is applied, we start trying to analyze for that torsion, we end up getting huge negative margins because the shear stresses are so high for a small amount of torque. But what that means is if we had also calculated the angle of twist, we would have found that that thing was too flimsy to pick up the load. Something else would have often picked up that load. So if we need to evaluate, well, how much torsion really gets into the part, you need to use the spring constant. Now, there's a couple principles involved, but the easiest way to do this is just to look at the angle of twist equation and to recall that the spring constant is just P over delta for an axial load, or T over theta for a torsional load. Therefore, we can just take T divided by the angle of twist, and that means that will be GJ over L is our spring constant. If we have other members attached, we can evaluate those spring constants, and that can help us to figure out how much torsion actually goes into these members. There's actually another principle in my older videos covered this, and I'll probably move this to a different video and lecture in class. But there's also something called differential bending. What happens is the flanges of a beam are relatively stiff for bending, and so if you have torsion and it's got a really low torsional rigidity due to the flimsy nature of these things, you'll end up carrying that load. Part of it, if there's nowhere else for it to go, is differential bending between the flanges. We'll save that investigation for another video. That's what this is starting to talk about. Okay, here's some quickie example problems. I think I only have one here. Here's a little angle, and we're looking for the maximum shear. Now, normally we're just looking for the maximum shear stress in the section. This may be a bad example because I'm asking you for the max shear stress in a particular flange. We're talking about the lower flange. As soon as you start learning about torsional stresses in run-round sections, you see that the max stress is actually going to occur in the upper flange. But we still will go through the process the same. This is our equation for shear stress. And this is our torsional constant. So we're going to go to our table. We will calculate our B and our T of each. That means the upper one is going to be, well, we're going to go construct a table. So our upper one is 1, right? Because it's 1.25 minus half of the thickness minus 0.05. So that's actually our first flange is 1.2, and the other flange is 1.1 minus 0.1. So this first term is the lower flange here, where this dimension is 1.0 and a thickness of 0.1. And if we take the B over T ratio, we'll find this is our alpha. And our other flange is 1.2 times 0.2 cubed. And we're going to take the B over T ratio, and we'll find that our alpha is 0.29. So the total J is this value. That's the J of the entire cross section. Now, if we wanted to calculate the max shear stress in this part, we would have then taken T of the thicker flange over J, but this problem is actually asking for the max shear stress in the lower flange, and so that means we're using the thickness of that flange to get the shear stress there. You got that? If we wanted the angle of twist, we then would calculate the J beta and plug it into this equation. Now the reason J beta, which I'm calling J theta here, and you'll notice I called J alpha J tau. There was a little while where I started using the tau and alpha as the subscripts for these terms. This J tau is just J alpha. This J beta or theta is just J beta. And the reason they're the same is because our B over T ratio for both of these flanges is down where the alpha and beta are basically the same value. Okay? That's a little example. That's how it works. You'll notice here this angle, 28.5 degrees. This means under this little torque, this thing rotates 28 degrees. You notice that means it's so flimsy, it probably is not going to pick this up unless there's nowhere else for that torsion to go. So that's a little video on the torsion of non-round sections. You're going to want to go back and make sure you understand torsion of round sections, and then this video, torsion of non-round sections, and then you're ready to go look at torsion of thin-walled closed sections. That'll be our next lecture. Enjoy.